Hello everyone, my name is Muzaffarjo Umidjonov. Welcome to my term project presentation for the special topics on electrical engineering and computer science course. My topic is scaling limits of ASAP7 FinFETs, where I investigate the impact of gate length scaling on device performance and analyze the associated process simulation toolchain. The primary objective of this project was to stimulate short channel effects (SCE) by physically scaling the gate lengths of an NMOS FinFET. I designed three distinct process splits: 24 nanometers, serving as the long channel control device; 18 nanometers, the nominal target for the ASAP7 node; 14 nanometers, an aggressive scaling target where we expect to see significant leakage and threshold voltage roll-off. To implement this, I developed a complete process flow using Angstrom-Craft. The flow starts with defining a 32 nanometer tall silicon fin, followed by shallow trench isolation fill and fin several steps. The critical variation occurs here during the dummy gate patterning step. By adjusting the lithography mask coordinates in the input deck, I created the three distinct gate lengths, while keeping the rest of the flow such as spacer formation and source drain epitaxy constant. As you can see from the code snippets, the geometry was successfully generated for all three splits. For the electrical characterization, I defined the mesh and physical models for G-device. I incorporated advanced mobility models, including Mujtaba and Canali, to account for high field velocity saturation. I also enabled Shockley-Read-Hall recommendation to accurately model sub-threshold leakage. The goal was to extract curves at a high drain bias of 0.7 volts. However, during the execution phase, I encountered a critical toolchain failure on the laboratory server. Despite successfully generating the process geometry, the handoff between Angstrom-Craft and G-device failed due to a server-side environment configuration issue. Specifically, the internal shell could not resolve the path to the G-device binary, and the parser exhibited version incompatibilities with the generated intermediate files. Rather than abandoning the study, I shifted my focus to toolchain failure analysis and theoretical physics prediction, which are valid outcomes in engineering. Based on FinFET physics, we can predict the behavior of the 14 nanometer device incorporated to the 24 nanometer control. First is threshold voltage roll-off. As we scale to 14 nanometers, the depletion regions from the source and drain encroach into the channel. According to the charge sharing model, this lowers the potential barrier, causing to drop by an estimated 30 to 50 millivolts. Second, in DBL, which means drain-induced barrier lowering, at 14 nanometers, the gate loses authority over the channel potential to the drain bias. We predict the dBL to speak from a healthy 30 30 MV in the control device to over 80 MV in the scale device, resulting in poor saturation characteristics. In conclusion, this project successfully demonstrated the process design kit implementation for scaled FinFETs. I mastered the Angstrom-Craft syntax for defining complex 3D geometrics and set up the correct physics for device simulation. While the server environment prevented the final 4 extraction, the study highlights the critical trade-offs in scaling. Shrinking to 14 nanometers Without concurrent channel doping optimization leads to unacceptable short channel effects. Thank you for your attention.